All right. So now we have the and then problem set 9 that was recently turned in. If you because it was due Monday, if you didn't get it in then because of what happened with class, just go ahead and get it to me as soon as you can. So that way I can have all of them back to you graded on Monday. All right. So
3.7 will be on the test or will not?
it will be. So I'm going to start that now, and I'll let you know what kind of problem can show up on the test. Okay. Okay, so now we're going to use solution techniques that we saw before for an application where you have a spring with an object attached to it, and the mass of the object is m, or it's possible that the weight, w, might be given. So for instance, the mass might be given in grams, or maybe the weight in pounds. So when it is just dangling on the spring, when it's at equilibrium position, the equilibrium length is L, that'll be expressed in whatever appropriate units of length. Okay. And U refers to, and that's going to be our solution to the differential equation you'll see in a moment, is the displacement of the object. And that is also expressed in whatever units of length. Be sure to keep the units consistent, like between feet, inches, etc. So where it's at equilibrium, which is what the picture reflects. So right here is where U is equal to 0. And we're using downward orientation because what's going to be interesting is when the, for instance, if we pull it downward to stretch on the spring. So down in this territory here is positive, and then U is negative, corresponds to up here. So our coordinate system is upside down. Okay. So we can use Newton's second law force equals mass times acceleration to obtain a second order differential equation that describes the displacement over time. So I'm actually going to do the left side first. The right side of Newton's second law, as normally written, is my left side for my differential equation. So I have mass times acceleration, which is u double prime, function of t. And then any forces acting on the object, we just sum up all these forces and we put them on the other side. So we have the force due to gravity, mg, and it's positive because gravity is acting downward, but downward is our positive u direction. Okay, so this refers to the weight of the object. So in other words, if you are given the weight, the object weighs so many pounds, you need to use the gravity constant to convert that to mass to use over here. Okay, so then we have Fs of t, which is the force due to the spring. And we have a description of that. So we have minus k, with k is the spring constant. L is the equilibrium length. And then we have u of t, the displacement itself. Okay. So in other words, it's u equals 0 is equilibrium. So this is basically identifies the total length of the spring as it is stretched at any time, multiplied by the spring constant. And we have this very important relationship that helps us solve for whatever constants we're going to need in our equation. And we have KL minus mg has to be 0. And all this is saying is when the mass is at equilibrium, the force due to the spring must balance out the force due to the weight of the object. So this relationship is often used at the start of one of these problems to, as you'll see in the examples that I'll do, to solve for certain constants that are not given. And then we have force due to any damping. And then any external force that might be acting on the object. Okay. Now, so to cut down the scope of a problem right off the bat for test studying purposes, external forces, that's actually the next section called force vibration. So I have it in the notes, but due to having a missed class, not going to cover it. It wasn't going to be in the test anyway. The homework set, problem set for this section is going to have problems either with or without damping, which certainly affects the behavior of the solution. But for the test, whatever problem you're given will not feature damping. So all this stuff is not on the test. We just care about these here. Okay. But the damping force is going to come up at some point, or today, tomorrow. That's equal to minus gamma, which is a damping constant. So gamma itself is positive, and yes, that's a gamma, not a y, times u prime. So we have a first derivative creeping into the equation from there. Whereas the external force could have whatever form. It's like the function g of t in your generic applicationless non-homogeneous equations. So the techniques for that, like undetermined coefficients and variation of parameters, would be used for that. Okay, so now what we can do is, now we have a form for all of these, or most of these terms, we go ahead and put everything together into a second order ODE that we can solve. And then from the solution, we can see how the object is going to behave over time. It's just dangling on that spring. So what we get is this equation, mu double prime plus gamma u prime, if there is any damping, plus ku, because what happens is there's a, because what I've done here is I've applied the relationship KL is equal to mg to get rid of the, to get rid of the mg term that's in there, is equal to whatever external force. And then we have initial conditions. So we have some initial displacement. And then we have, because it's a second order equation, of course we have two initial conditions. So the condition on the first derivative, that would be z naught, and that refers to the initial velocity. Now, what will happen on the test is you'll see this in the practice test. You're given a problem that describes in words what the situation is of this object on the spring, and given its mass or weight, maybe something about its equilibrium position. So whatever constants you are given, you use that to figure out everything else to get boiled down to a problem like this. Now on the test, again, you won't have this and you won't have that. So I'll describe the simple situation first and go from there. But it's important to understand from the verbal description of a problem what the initial conditions are supposed to be. So to give you an example from the examples that we have here. So this initial displacement would be non-zero if, for example, if the object is pulled down, because we are giving some initial displacement to it. On the other hand, this would be equal to 0 if it is stated somewhere where the object starts motion from equilibrium. Okay. Now, as for the initial velocity would be equal to 0 if the object is set to be simply released or let go. In other words, you might pull on the object to a certain extent and say, okay, now just let it go and see what happens. So you give it initial displacement to it, but not any initial velocity. On the other hand, this would be non-zero if some initial velocity is applied to the object in a certain direction. Keep in mind, positive would indicate downward, and negative would be upward in our orientation that we're using. Okay. So, it's kind of like when you're in a foreign country and you have your phrase book for certain common phrases. That's kind of what I'm giving you here for these problems. What are the phrases, wording in the problem tell you about the initial conditions that you're going to have? Okay. So now we're going to take a look at the behavior for the simplest case, and this is the kind of case that you'll see in the test where there's no damping and there is no external force. I'll remember to take 10s today. So gamma equals 0, and external force F of t equals 0. See how the solution behaves in that case. Why am I holding two pieces of drawing? Okay. So what happens in this case, your equation reduces to mu double prime plus ku is equal to 0. So you solve this like in an error situation. You have your characteristic equation. What is the characteristic equation in this case? mr squared plus k is equal to 0. Okay. So what are roots going to be? Well, first, are they going to be real or complex? They're going to be complex. So I'll just throw it out. It's going to be plus or minus something times I. What's the something? square root of k over m. Yeah. Because you get r squared is minus k over m. Then you take a square root, and that's where the plus or minus I appears. And I'm going to, as a new notation, I'm going to abbreviate this. So plus or minus omega naught times I, where omega naught is predictably square root of k over m. And this is of interest because this is called the natural, also known as the simple frequency. So it's a frequency at which the object is going to oscillate. Now, when you have these kind of complex roots, well, we want a general solution. So, like in all cases, regardless of what your roots are, you can have a constant times one solution plus a constant, another constant times another solution. So what kind of solutions do we have when we have roots like this that are purely imaginary? What kind of functions do we have? Sine and cosine. So if I fill in cosine of what? Omega naught t. I think I heard someone say. And then sine omega naught t. Okay, so this is the general solution. And then, like usual, you would use your initial conditions if given to find C1 and C2. Okay. Now, I'd like to be able to understand the behavior of a solution qualitatively. And for that, I'm going to assign some values to these constants, C1 and C2. So let's C1. I'll use a capital A and capital B in the notes, but you guys are used to C1 and C2. I'm going to call this R cosine, that's a lowercase delta, and C2 is R sine delta. And I'm going to plug those into my solution. So UT is R cosine delta cosine omega naught t plus R sine delta sine omega naught t. And the reason I'm doing that, seems like a strange thing to do, it sets me up to be able to use a trigonometric identity. Cosine of a difference. So when you have two cosines plus two sines of the same angles, that's a cosine of a difference. So, so I'm using one of the essential trig identities. You all know cosine squared plus sine squared equals 1. I would say that that's actually a special case of this one. Cosine A, cosine B, plus sine A, sine B. I'd say that in more advanced situations, this one just seems to come up so much more often than many of the other ones. Okay. And the thing is, you get A equals B, you get cosine squared plus sine squared equals cosine of 0, which is 1. So, what?
Oh, excuse me.
Okay.
Okay.
All right. So we have, well, R is factored out. So we get cosine omega naught t minus delta. Now, the way I wrote it, I could have said delta minus omega naught t. Doesn't matter because cosine is an even function. You negate it, it doesn't change anything. Okay, so now as for why the solution is written in this form, that's useful to us because R, if I were to take the both these equations and square them and add them up, what you find is that r is the square root of c1 squared plus c2 squared. So after you find c1 and c2 in the usual way, with your initial conditions, you can use those values to get r. And r is the amplitude. Maybe you have fond memories of some lower level class of graphing sines and cosines, and either finding or using the amplitude, period, and phase shift. Does that ring a bell? Yeah, it is kind of tedious. What does the amplitude mean? Yeah, so you have this wave that's oscillating infinitely, and r is the height of a wave above the equilibrium position. So this is the maximum displacement that you're going to get, because what's going to happen in this case with no damping, no external force, the object is going to oscillate forever between plus and minus r, displacement from equilibrium. Okay.
I have a question.
Yeah.
This general solution, is that just for complex roots? Like with a imaginary?
Yeah, if they're purely imaginary. Like even if you have complex numbers, but if there's a real part, I'd still have exponentials here.
Okay,
Yeah. And we're going to see that when we look at damping. Now, okay, so once you have C1 and C2, you can get the amplitude. What you can also get is tangent of delta is equal to C2 over C1, and that is called, so delta is called the phase, also called the phase angle. Okay, so it gives you an idea of, because this endless wave, what's the starting position of a wave, for instance, at t equals 0. Okay. Also, if I define capital T to be 2 pi over omega naught, which also becomes 2 pi square root of m over k, that is the period. So ordinary sine and cosine have a period of 2 pi, but this is what the period is going to be in this case. So if you were to compute your solution like you normally do, then go ahead and use C1 and C2 to get the amplitude and phase angle, and also use omega naught to get the period. Then what happens is you can graph a solution, like you used to do, like you've given the period, amplitude, and phase shift. Okay. So what I would ask for in a test is, using whatever I would give initial conditions in that case, go ahead and come up with a solution. But these quantities would also be asked for. And probably very amusing for me to also require a graph, but I try to be a little bit merciful.
Thank you for that.
Maybe do as a bonus. I've gotten some very interesting doodles on tests over the years. Something all scary, but okay. All right. So, any questions about the solution in this case, or the parameters that are involved? Okay. So, even though we have 20 minutes left, that comes to an end. Any material is actually going to be on the test. But I still need to talk about more that can be on the homework with this section. Now I'm going to include damping. Well, actually, I do have an example coming up a little later on of what I've just shown here. Okay. So, if there's damping, your equation is mu double prime plus gamma u prime plus ku is equal to 0. We're still assuming no external force. So now your characteristic equation is mr squared plus gamma r plus k is equal to 0. And now you go ahead and solve for that using a quadratic formula. So your roots, lambda 1, lambda 2, turn out to be so minus gamma plus or minus square root of gamma squared minus 4mk all over 2m. Okay. And depending on, it all depends on what the values of the constants are. Gamma, mk, we could have distinct real roots, we could have complex roots, we could have repeated roots. So let's look at all these possibilities. Okay. So for instance, if the discriminant, so gamma squared minus 4mk is positive, so we have real distinct roots. So this is a case where it's strictly positive. Well, you know what form a solution has in that case. So we have your solution is some constant e to the lambda 1t plus some constant c2 e to the lambda 2 t. Also, what happens is, okay. Because all of the constants, gamma, m, and k, are positive. So, okay.
Dr. Lambert.
Yeah.
What's that in front of the gamma squared?
A 1. I'm numbering scenarios.
Okay.
Yeah. Okay. Yeah, there's going to be a 2 and 3 here. Okay. Now, okay, I'm going to do something I shouldn't do, and that is go off script a little bit. Because what's important to understand from this solution is, are the roots positive or negative in this case? Now, here we have the gamma, mk themselves are all positive, so for instance, this is negative here. So I choose a minus sign, obviously that's going to be negative. But what about the plus sign? So is minus gamma over 2m plus square root of gamma squared minus 4mk all over 2m positive or negative? Because this is certainly negative, but what if this is large enough that it could offset it and give you a positive result? So what I'm going to do is I'm going to take the 2m in the denominator here and move it inside the radical, which means it's going to become 2m quantity squared. So this is equal to minus gamma over 2m plus square root of gamma squared minus 4mk all over 4m squared. And if I break this up, so I have gamma squared over 4m squared, but that's the same as gamma over 2m quantity squared. And then what's left is I have minus k over m. Okay. So what I can, oh, interesting. In the notes, I have a 4 up here. It's not supposed to be there. It's supposed to cancel with the 4 down below. So I need to remember to fix that. So from this, we can actually conclude that this whole thing is negative. And the reason why is because since these quantities are the same. So, and this whole thing underneath is positive. So what the idea is, this whole thing is going to be slightly less in magnitude than gamma over 2m because we're subtracting something from it. K and m are positive. So the result is both roots, if they're real, they're distinct, they're also negative. Therefore, we can conclude that this whole solution goes to 0 as t goes to infinity. So if the damping constant is large enough, what happens is you don't see any actual oscillation, which is what you'd expect normally. That there be some oscillation and eventually settles back down to equilibrium. But here the damping is so strong that it just, the displacement is a case of nothing, it just slides back to equilibrium in a non-oscillatory way. All right, so that's scenario number 1, distinct real roots. If we have the discriminant is equal to 0, we get repeated roots. So our solution has this form, a constant e to the lambda t, where lambda is the one root. So lambda turns out to be minus gamma over 2m. And then the other term is, bless you, t e to the lambda t. And this one root is negative, again. So this also goes to 0 as t goes to infinity. So again, there's no oscillation happening over time. And then finally, if a discriminant is negative, then we get complex roots. And our solution has this form. We have an exponential that's minus gamma over 2m as a coefficient times t, cosine of, and I'll abbreviate, mu t times c1, plus another constant, same exponential, sine mu t, where mu is just the rest of the root, the imaginary part. So, whoops. Sorry to anyone who's been watching. So, mu is just square root of 4mk, well, actually I need to keep it positive, so gamma squared minus 4mk all over, I do need to negate it. 4mk minus gamma squared all over 2m. So that's the coefficient, that's the imaginary part of a root that goes into the sine and cosine. So here we do see oscillation, but again goes to 0 as t goes to infinity, just in an oscillatory manner. So the damping constant is, this happens when the damping constant is smaller relative to the other quantities, k and m. So what happens is it's just going to keep oscillating, but less and less over time until it settles down in its equilibrium position. So in all cases, the object returns to its equilibrium position. It just gets there in different ways. You can imagine if there was a positive real root, we'd have a problem, a very non-physical situation, because that would mean the oscillation would keep going larger and larger, going off to infinity, and your spring would stretch infinitely. And that makes for pretty cool sci-fi, but unfortunately, the math doesn't allow for it. Alrighty. Now, in this complex case, okay, so I don't want to go to another board yet. So continuation of that. This quantity, 2 pi over mu, it's because before I took 2 pi over omega naught and computed the period. That is called the quasi period, because what happens is the object appears to oscillate with that period over time, even though it's not strictly a periodic function per se, because of the effect of the damping. But I should mention, as gamma, if a damping constant goes to 0, the quasi period, or the quasi frequency, approaches the natural frequency, and you get the actual period that you have in the no damping case. You can see that here, that if I were to let gamma go to 0 in this expression, what you get is square root of k over m, the natural frequency that I have written over there. Okay. So those are the three situations of interest when you do have damping, but I imagine what you guys are interested in is a case where there is no damping. So we'll take a look at an example of that before we stop. Then on Friday, I'll start with another example that does have damping. And then we'll have the rest of Friday and all of Monday to discuss the test. So be sure to look at the practice test if you haven't already.
So the exam has not been moved.
April 5th. I mean, when I talk about pushing it back, that was from the original April 3rd that I announced at the beginning of the semester to April 5th. So there's no need to push it back further than that. Okay, so we have our object has a weight of 16 pounds, and it stretches the spring 3 inches. I'm going to work in feet though, so my L is so 3 inches, so it's 1/4 of a foot. Okay. Oh, dang it. Look at the wrong example. 2 pounds. Stretch the spring 6 inches, so 1/2 a foot. My eyes scrolled down too far. Okay, so it's pulled down an extra 3 inches. So it starts at equilibrium, but you pull it down 3 inches more. And then it is released. This is where you consult your phrase book that I described earlier. So what is the displacement over time? What is U of t? Okay. So what you need to do is, and we're also assuming there's no damping. So your equation is going to have this form: mu double prime plus ku is equal to 0. And we have initial conditions. Now, because it's simply released, there's no extra velocity imposed on it. That means that u prime of 0 is 0. So we go ahead and fill in 0 here due to being released. And then what about the initial displacement? But what should I actually write down for units? 1/4 of a foot, 3 inches. Okay. All right. Now, we need mass and we need K. We don't have either one just yet, but to get the mass, we have a relationship weight is equal to m times g. So we just get m is equal to w over g. So the weight is 2 pounds, and then we divide by our gravity constant. So that is 32 feet per second squared. So we get 1/16. So that is our value of m. And then the only thing that's left is k. And to get k, we use this equation. KL is equal to mg. We know what L is. It's 1/2. And mg is for weight. So k is equal to mg over L. So I can fill in 2 pounds for weight, and then half a foot for the given equilibrium length. So we get 4 pounds per foot. So, so now we have all of the constants. So our equation has this form: m is equal to 1/16 u double prime plus k, which is 4 u, is equal to 0. And then we have our initial conditions. But keep in mind that this is a problem of no damping. We know what the solution looks like. The form of the general solution is C1 cosine omega naught t plus C2 sine omega naught t. But omega naught is the square root of k over f. And we can just go ahead and fill in those values. So we have, I have 2 minutes. So we have 4 over 1/16, square root of 64, which is 8. So, okay. So now we can fill that in here for a solution. And then we can use our initial conditions to get the solution. So u is 0 is, we just plug in t equals 0, all we get is C1. U prime of 0, when we differentiate this, what you're going to get is, if you plug in t equals 0, here you get a sine. That's going to give you 0 when you plug in t equals 0. And then here you're going to get a cosine. So you end up with omega naught C2. But C1 is supposed to be 1/4, or this is supposed to be 1/4. U prime of 0 is supposed to be 0. So that tells you that C1 is 1/4, C2 is 0. So our solution turns out to be 1/4 cosine 8t. That describes the displacement over time. Okay, so I have a little more to finish with this example, and this is on page 68 in the notes. It's all worked out there. So finish off a problem on Friday, starting on Friday with the period, amplitude, phase angle. Okay.